Hello everyone. This is the second session of the your mechanics of composite materials, elective one of the elective, and today I am going to continue to the next derivations related to the micromechanical analysis of lamina. So previously we have seen the longitudinal length modulus as well as one volume fractions and density, volume fraction, mass fraction, density in terms of mass fraction, density in terms of volume fraction. Okay. Now today we are going to go to the next subsequent constants related to the composites. So here you just to note that we are having the four basic elastic moduli. In that the first one what we have derived is Young's modulus, that is in the direction of the fiber. That's what longitudinal Young's modulus. So that is along the direction of fibers. If you want to calculate the Young's modulus, that is you will always E1 suffix E suffix 1. And what about transverse direction? Okay, that we are going to find out today. So this is all derivations related to that. Okay. Transverse Young's modulus. So transverse means perpendicular to the fibers of the composites. Okay. So where the composite is loaded in the direction of the transverse location. So it is load is acted perpendicular to the fibers. Next. The next assumption that I am going to take here is the fibers as well as the matrix are again represented in terms of the rectangular blocks as we done in the previous derivation. Okay. Here one more thing is, okay, if you apply the load in that directions, which is schematically we can represent in this way, load is exactly in this direction. Okay, that is transverse direction. Load is this location, we usually call it as transverse. And after that, all the notations which is similar to the previous derivations, where H represents the thickness and TF represents thickness of the fiber, TM represents thickness of the composite or matrix, TC represents the thickness of the composites, and sigma C represents the composite stresses. Okay, stress developed in the composite. Now, from your basic understanding, if I apply the load in this direction, since the cross section is same for matrix as well as the fiber, stress developed in composite is also same as stress developed in the fiber as well as stress developed in the matrix, because cross section of the composite, fiber, matrix all are same and the load is also same. Okay, that's why the first derivation that I am going to get from the basic mechanics of materials. And after that, this is what the notations represent. Sigma C represents stress in composite, fiber and matrix respectively. Next, what about deflections? Let us observe that deflection in a transverse direction. Okay, so I want to calculate the deflection in the transverse direction, that is in this direction only. So which is nothing but let's look into the composite prospects. Delta C, which is nothing but the deflection considered by the matrix plus deflection developed in the fiber. Okay, so that's what the relation that I am going to get, where delta C represents the sum of the transverse extension of the fiber and the matrix. So I always remember that delta C or delta represents deflection in transverse direction. Okay, that is along the direction of the say coordinate 2. So two relations I got, you just remember, stresses developed are equal and deflection is nothing but summation of all this. Since I want the transverse Young's modulus, okay, next what I can do is by using the definition of normal strain, I can represents the deflections. So from our normal strain formula, strain is nothing but change in length by original length. So change in length is nothing but delta C. So delta C is equal to original length, that is thickness of the composites. Okay, so thickness of the composites multiplied by strain of the composite, that is epsilon C. Similarly, I can represent that for fibers also. Delta F is equal to original length multiplied by strain, and for the matrix delta M is equal to original length, that is thickness of the matrix, and strain of the matrix, where T represents thickness, okay, and epsilon represents transverse strain. So observe that the strain in the transverse direction we cannot call simply as a strain from now onwards. Anywhere, whenever you define stresses or strains in this module, so we usually go for which direction. So this is in the direction transverse. And by using Hooke's law, we can also represent the strains in terms of stresses. Okay, so what is that? Epsilon C is equal to sigma C by E2. Since it is in the transverse direction, so I am going to denote the Young's modulus, corresponding Young's modulus of the composites by say E suffix 2. Okay, this is what we need to calculate. And similarly, I can define the relation for the fibers also. Epsilon F is equal to sigma F by EF, and for the matrix epsilon M is equal to sigma M divided by EM by using your previous relations. All these three things I am going to substitute here right now, and once you substitute that, it becomes sigma C divided by E2, sigma F divided by E2, sigma F divided by EF, and sigma M divided by EM. And once you substitute that in the equation number 3, later I am going to substitute equation number 3 in equation number 2. Okay, so if you do all these things together, so it becomes of this format. Since it is 1 by E2 along with the thickness TC, okay, that is equal to 1 by EF TF plus 1 divided by EM TM. Since thickness C I am going to divide throughout the equation, it comes in the denominator on the RHS, that is TF divided by TC, TM divided by TC. Okay, so once again, if you observe this relation TF divided by TC is nothing but if I multiply this along with its length factor, it becomes the volume fractions of the what is that? The particular composites. So that it becomes TF divided by TC becomes VF, TM divided by TC becomes VM. That is volume fractions of fiber and matrix respectively. Okay. So finally the relations will be, which is of this form, 1 divided by E2 is equal to VF divided by EF plus VM divided by EM. Okay. So reciprocal of the transverse Young's modulus is equal to relations summation of ratios of volume fibers to volume of fibers to Young's modulus of the fiber, volume of the matrix to Young's modulus of the matrix. Okay, so this is about the transverse Young's modulus derivation for an composite material. Okay, so longitudinal Young's modulus means when the load is applied along the direction of fibers. Transverse Young's modulus means when load is perpendicular to the fibers. So you should be aware of these two things. So E1 is VF EF plus VM EM, but E2 is in order to calculate E2, it is 1 divided by E2 is equal to VF divided by EF plus VM divided by EM. So this is about one more constant, elastic constant for the composite material. Next, another one that will come across here is major Poisson's ratio. Okay, so before getting to that, what is that major Poisson's ratio? Let us look into the Poisson's ratio along with the this one. What is the main difference between this? So Poisson's ratio is nothing but transverse strain to the longitudinal strain. Here also the same relation is applicable. So I need to find out the Poisson's ratio based on this definition. That is, it is a negative of the ratio of the normal strain in the transverse direction to the normal strain in the longitudinal direction when normal load is applied in the longitudinal direction. Okay, so that is, I will explain this part into the figure. Okay, so whenever the strain is developed, we know that when the strain is perpendicular to the surface, it is usually called as normal strain. Okay, that's what he is talking. And when the load is applied in the longitudinal direction, that is, when you are going to apply the load along the direction of the fibers, okay, there are strains induced in longitudinal direction, that is normal strain, and transverse direction. If you take these two ratios, then we call that as major Poisson's ratio. So that's what which is denoted in the next sentences. Composite is loaded in the direction of fibers, and fibers matrix are again represented by rectangular blocks. This is once again the assumption. Okay, so let us have the definition once again with respect to this figure. So if I apply the load in this direction, this is what the longitudinal direction. There are strains developed in this direction also. Okay, that is what you can represent as say E1, here as say E2. So when I take these two ratios, this is normal strain. Why is normal strain? Because it is perpendicular. This one is also perpendicular. And one more thing is they are talking that this is as transverse strain, transverse normal strain. This is as longitudinal normal strain. So if I take these two ratios, transverse normal strain to the longitudinal normal strain, then we call that as a major Poisson's ratio. And also the load is applied along the direction of fibers. Okay, so you should take care of all these things. Next, for this case, so obviously we have to go with the in-depth definition of the strains. Strain is nothing but change in length, that is the composite deflection delta, and fiber deflection, matrix deflection will arise. So we should use these parameters for our derivation part. So let us look into the transverse direction of the composite. Deformation in the transverse direction as delta C, and transverse deformation as delta F, and transverse deflection for the matrix as delta M. Means all these things are found in this direction. Okay, so if I go for its top view, you can observe in this view. Okay, if I look into its coordinate system, this is coordinate 1, this is coordinate 2. Okay. This is coordinate 2. So in the top view also you can go for the same thing. This is coordinate 1, this is coordinate 2. So all these deflections are taken in the direction of 2, that is transverse direction. Delta C is the deflection in the transverse direction, okay, of the composite. That should be equal to the deflection of the fiber in the transverse direction and deflection of the matrix in the transverse direction. Okay, so that's why superscript is also given in terms of T. Okay, so you need to take care of that. Once again, if you want to frame the equation, so in the direction of 2, the composite deflection is nothing but deflection of the fiber plus deflection of the matrix. Okay, that's with the superscript T. Okay, so always remember this. This is from our basic understanding or basic assumption. And let us look into the normal strains in the direction of the transverse. Okay, so epsilon F T F suffix of the fiber is equal to delta F the transverse direction divided by thickness of the fiber. So change in length by original length. So change in length is delta ft, original length is tf. That gives you the strain in the transverse direction. Similarly, strain in the transverse direction for the matrix delta suffix m superscript t divided by tm, thickness of the matrix. And similarly for the composites also, delta ct c divided by tc, where these strains are the transverse strains in the composite fiber and matrix respectively. Okay. Next, what I can do is I can substitute the equation number 2 into the equation number 1. Okay. So if then it becomes the product of strain into thickness. Okay. So in this equation, so Tc into epsilon Ct is equal to Tm Emt plus Tf epsilon F into epsilon F superscript T. Then let's call this as equation number 3. So I want to find out the Poisson's ratio. Since you want to find out Poisson's ratio, now I should replace the strains, that is epsilon C, epsilon M, and epsilon F in terms of Poisson's ratio. So if you do that, we should go for the definition of the Poisson's ratio for the composite matrix fiber individually. So if you apply that, Poisson's ratio nu f is nothing but the transverse. So we should take care of this one. So from the definition, transverse normal strain to the longitudinal normal strain. Okay, that's what which is written here. So Poisson's ratio of the fiber is equal to negative of minus transverse fiber strain divided by longitudinal fiber strain. Similarly, I can go for the matrix. Poisson's ratio nu m is equal to minus mu epsilon of the matrix in the transverse direction divided by longitudinal direction strain. And finally, it comes with the composite Poisson's ratio. Okay, that's what which is denoted by mu12. It is mu, not mu c. So instead we are represented that as mu12. Okay, because it is in terms of 1-2 direction. Okay, so it is in terms of 1-2 direction. So therefore, similar relation that we need to observe, that is transverse strain to the longitudinal strain. Once you develop these equations, let's call this as equation number 4, and after that, I want to replace the transverse parameters so that it becomes mu f into epsilon f longitudinal, mu m into epsilon m longitudinal, mu12 epsilon c longitudinal. So if you substitute that, then it becomes the equation becomes is of this form. So here, one thing you need to note down is the strain in the, what is that, L represents the strain in the longitudinal direction, that is in this direction. So here you should observe that the deflection in the, this one, deflection, so it should be straight. Okay, the deflection in the longitudinal direction, or the strain in the longitudinal direction, is same for composite, fiber as well as matrix. Okay, so that is epsilon c, epsilon m and epsilon f are equal. Okay, and these are all the indications. So these strains are equal. So since these strains are equal, we can terminate that as well as with the negative sign. So finally what we will going to get, and comparing that with the previous one, Tm divided by Tc and Tf divided by Tc is nothing but the volume fractions. So finally, so if I terminate all these quantities and divide the whole equation by Tc, so I am going to get the equation mu12 is equal to mu m into volume fraction of the matrix plus Vf into UF, that is volume fraction of the fiber multiplied by Poisson's ratio of the fiber. So this derivation gives you what we call the major Poisson's ratio. Okay, so this completes the one more elastic moduli derivation. Next, we will go with the fourth one, that is in-plane shear modulus. So when you look into the previous constants from your mechanics of materials, we are having Young's modulus, then Poisson's ratio, then shear modulus or modulus of rigidity, that is the quantity G. So now I should calculate the quantity G for the composites. So in order to do that, let us apply the shear stress tau to a lamina as shown in the figure. For this case also, we are going to observe the fiber matrix are represented in terms of rectangular blocks. Okay. So like this. So tau which is applied not tangential to the each surfaces, and we are taking it as a composite in terms of the rectangular blocks only. And because of this, obviously you are come across with the shear deformations delta C, delta F and delta M. Okay, so what are these things? Let us look in with the next relation. So here also by using our basic superposition actions, composite deflection is nothing but matrix deflection plus fiber deflection. Okay, let us call this as equation number 1. From the definition of shear strains. Okay, so what is shear strains? It is nothing but the change in length by original length. We will adopt the same thing. Delta C is equal to, that is change in length is equal to gamma. Okay, only thing is we are changing the strain notation, that is gamma C into T suffix C. Similarly for the fiber, delta F is equal to gamma F into TF. Delta M is equal to gamma M into TM. Okay, this is by using the basic equations that we adopted for the shear strains. Now what I can do is I can substitute this into the equation number 1. So if you substitute that, then it becomes gamma C into TC is equal to gamma M into TM plus gamma F into TF. So after this, I know that there from the Hooke's law, there is a relation between the shear strain to the shear stress. Okay, let us look into that. That is gamma C is equal to tau C divided by G12. Okay, as we know, we want to find out the shear modulus of rigidity, that is G. Since it is in the direction of 1, 2, okay, since it is in the direction of 1, 2, so it is represented as G12. Gamma C is equal to tau C divided by G12. Okay, similarly, gamma F is equal to tau F divided by GF, and later on tau gamma M is equal to tau M divided by GM, where suffixes are used. Okay, next what I can do is I can substitute gamma F, gamma M and gamma C into the equation number 1. Okay, so if you substitute that, then it becomes tau C divided by G12 into TC, tau TF divided by GF into tau F plus TM divided by GM into tau M. Next, what simplification I can do is, if you look into the the shear stress values, these shear stresses are equal. Okay, because they have been throughout it's a plane surface. So once these shear stresses are equal, I can terminate all these, and if I take TC into the denominator on the RHS, then it becomes TF divided by TC, TM divided by TC. So that those relations are nothing but These relations are nothing but the volume fraction of the fiber and matrix respectively. Okay, so if you go through that, we are going to get 1 divided by G12 is equal to Vf divided by Gf plus Vm divided by Gm. Okay, where Vf represents the volume fraction of fiber and capital Vm represents volume fraction of the matrix, where G12 represents the in-plane shear modulus. Okay, so this completes the derivation of for in-plane shear modulus and 4 elastic moduli. Okay, and thank you everyone for your patience listening. So hope everyone will cover these portions and looking into the next subsequent problems that I am going to conduct in the future classes. Okay, thank you everyone.